Welcome back to this second video on rules of derivatives. Like usual, let us actually take a look at a quick review of what we saw in the last video. So we actually covered already four rules. The first one, if you actually derive a constant, thou shalt get 0. If you derive x alone, what will you get? Who remembers? If you derive x alone, yes, you're going to get 1. Good. If you derive a combo of a constant that actually multiplies x alone, so something like 7x, what are you going to get? You're going to get just the constant itself. And the fourth, the last but not the least, if you derive x to a power of n, what happens to that? Remember the rule, we take the n, we bring it in front of the x, and we subtract 1 from the power of n. So the n goes in front, and the power becomes -1. Good. Okay, so today we're simply going to advance into more rules of derivatives, including this one. So rule 5. In rule 5, I would like to actually find the derivative of a constant. Let's call it k this time instead of the c that we had before. Again, c and k will always stand for a constant. And I actually would like to find the derivative of a constant multiplying any function. We will actually show that this is equal to the constant outside and the function derived. You see what's happening here? It's kind of a subtle thing. This is the derivative of a constant multiplying a function. What I'm saying this is equal to is the derivative is applicable to the function but not to the constant. Yes? So before I actually prove this to you, let me give you an example. Just to be clear about what we're going to be doing here. Okay, so something like find the derivative, find the derivative of, let's call it j of x. Let's give it another name. You'll see why I'm calling this j of x in a minute. Find the derivative of j of x is equal to 7x3. Okay? So you will notice here that I have a constant that actually multiplies a function. This is my k. This is my f of x, right? So I'm really multiplying a constant and the function. The constant is 7 and the function is x3. According to the rule I've just put on the board, according to this rule, when you multiply a constant and a function and you want the derivative of this outcome, you should disregard the constant and only derive the function. So if I apply that rule, the derivative of j, which of course will be the derivative of 7x cubed, should be, let me follow that rule to a t. I'm going to take the constant out. Here's my k. And look at the prime being attached to f. So look at the prime being attached to the x to the power of 3. And then I try to think, do I know a rule for this? Of course I do. Rule number 4. The derivative of x to the 3 is like x to the n, where n is 3. So what is this? This is 7 times what? Well, if the n is 3 and it goes in front and it's subtracted, then we should get 3x to the 3 minus 1. That should be my answer. Yes? And that should be 21x squared. Yay. Once again, please consider the huge advantage of having this rule to play with rather than finding the derivative of 7x cubed using the limit definition. For the limit definition would actually be quite tedious. I mean, we'd have an x cubed, that means we'd have an x plus h to the power of 3 at some point. That would turn out to be probably a messy derivative to take. But this rule brings us to the answer right away. And then basically we can just conclude that the answer is 21x3. Good. Okay, so that's how the rule goes. Let us see if I can convince you that this rule is actually valid. We'll erase this now in 2, 1, 0. All right. All right. So, proof. Proof of that rule. Okay. So let j of x, see I'm using that same notation as before. So j of x is going to be k f(x). Okay. So the question is, what is j prime? What is the derivative of j? I.e., that's Latin for id est, that is to say, c'est-à-dire, i.e., that is to say, what is j prime, but j is k of x. So really, I'm actually asking what is the derivative of k, a constant, times f, a function. All right, so when we actually go to a proof like this, we need to go back to the limit definition. So j of x prime, that is equal to the limit as h goes to 0 of, okay, I'm used to having an f here, right? Now this is a j, so just modify the formula accordingly. So that'll be j of x plus h minus j of x all over h. Lovely, lovely, lovely. All right, as usual, we're going to start with something easy. We're going to replace j of x. Where is j of x on this whiteboard? Right here. J of x is k fx, f of x. Now the question is, attention, what is j of x plus h? Well, if j of x is actually k of x, then if I want j of x plus h, I am going to have to replace the x with x plus h. So I'm going to have to replace x with x plus h. So j of x plus h is k multiplied with f of x plus h, simply by here replacing x with x plus h, and here too. Now, what is this? What is this? This is the limit as h goes to 0. What do you see in here, folks? What do you see in this numerator that I could potentially factor out? A k? Good idea. Let's factor out a k. I factor out a k from here and here. I'm going to get f of x plus h minus f of x all over h. My next move will be this. I am going to take the k out of the limit. That's because the limit of k times something is equal to k times the limit. So here's k outside of the limit. This is a limit rule. This is a limit property. And basically what am I left with is this. Limit as h goes to 0 of fx plus h minus fx over h. Now, pay attention to this for a moment. I think we've seen that before many times. What is that? What is this guy? Limit as h goes to 0, fx plus h minus fx over h. Yeah, clearly the proof is complete because this is f prime. The proof is complete. QED. QED, which stands for Quod erat demonstrandum. It is demonstrated. It's over. Good. So we now know for sure that, what's the conclusion to this? We now know for sure that, like we have established before, the derivative of k times fx is actually, you can take the k out and really just find the derivative of f itself. Quick example on how this works. Again, find the derivative. So let's just put as a prime like this. Find 6 over 7 x to the 7 prime. Okay, so I think quite clearly that this is my k and that this is my function, because a function has to have an x in it. If it doesn't have an x, we call that a constant that we either call c or k. So my rule says you can take out the constant and you should focus on the derivative of x to the 7. See how this goes? The 6 over 7 goes out. No derivative to the 6 over 7. Only derivative to x to the 7. All right. What is the derivative of x to the 7? Well, that is 6 over 7. What is the derivative of x to the 7? Rule 4, right? Rule 4, x to the n. So how does that go? I bring the 7 right in front, and I subtract 1. Final answer for this, so égal, equal, what do we get for this? Ah, I see a little simplification here that can make my life a little bit better. Bye with the 7s, and I am actually left with 6x to the 6. That is the derivative of 6 over 7, x to the 7, and that actually demonstrates the point. Good. I'd like to do one more example on this before the next rule, so I will erase this now. If you're not done, you can pause. Okay. All right. So another example here on this could be find or evaluate. What could we have here? 11 over 4x to the power of 3, and I want the derivative of this weird expression. So 11 over 4x3. That is supposed to exemplify the rule we just saw, the k times fx rule, right? So does it actually do that? Is it in the form of a constant multiplying a function? Not quite. Can we make it look so? Can we make it look like kfx? Well, isn't this 11 over 4 times 1 over x3? Can I write this as that? I think I can, because we know how to multiply fractions. So 11 times 1 is 11, and 4 times x3 is 4x3. But you see, the advantage of this is that it can now become 11 over 4 times x. Oh, look at that. x to the negative 3. Ah, and now that is a k times an fx times the function and times. So I can apply my rule because I have a constant that multiplies something with x's. Okay, so what's the rule here? Well, the constant goes out, very nice, and I need to derive x to the minus 3. Not difficult at all. Again, rule 4, I'm going to bring my exponent in front and I'm going to subtract 1. That's right, so the negative 3 goes in front and we go n minus 1, just like rule 4 has taught us. So this is 11 over 4 times minus 3, x to the minus 4. We are not big fans of negative exponents. Negative exponents induce errors later on in the course, so we're going to learn to get rid of it completely. That's 11 over 4 times, watch it here, only the x has a negative exponent, not the minus 3. So the minus 3 stays up, but the one that goes down is x to the minus 4. And of course, it becomes x to the 4. And we have gotten rid of the negative exponent. All this is nice, and it actually gives me minus 33 over 4x4. That is the answer to the derivative of 11 over 4x3. Okay, so I think we have enough examples of this. Let us move on to rule number 5. Let's get rid of this, so if you're not done, pause, and I'll see you on the other side of the pause. All right, back from the pause. Rule number 6. Rule numéro 6. This one is about adding or subtracting. So plus or minus two functions. What is the derivative of something that consists of the sum or the subtraction of two functions? Well, if we're guided by our most elementary intuition, we're thinking perhaps we should take the prime, give it to this guy, and give it to that guy. Is that true? Does that work? The answer is absolutely. This is equal to f prime plus or minus g prime. I will prove this to you before the end of this video, but first I would like to show you an example on how this works. So example, find the derivative, of 1/2 x squared plus, what shall we get here, 2/3. Let's put the root x downstairs to make things a little more complicated. Find the derivative of this function. So 1/2 x squared plus 2 over 3 root x. Okay, so this is our most difficult problem so far in this section. Now, you notice that in this problem, there is a plus right there in between. You know what that means? It means that the first function right here is going to be our f, and the second function is going to be our g. So that what we have is we have f plus g. So truly, we need to apply this new rule, the newest of our rules, which is the sum or the subtraction of two functions. So what does that mean? It means that 1/2 x squared plus 2 over 3 root x, if we want the derivative of this, what are we going to have to do? We're going to have to, like here, give the prime to the f and give the prime to the g. So this is 1/2 x squared with the prime, and this is 2/3 root x with the prime as well. Okay, now how do we do each one separately? Oh, well, then there is something called Rule 5 here that can be applied because this is a constant times a function. So we have used here, this is rule 6, and here we're going to use Rule 5. Not once, but twice, because we have a constant times a function, and here too, a constant times a function. So that would mean that this would be equal to 1/2 out, no derivative, and x squared with the derivative. And here it would be 2/3 out, this is my constant, and 1/root x derivative. Good. Okay, so this is Rule 5. Now, I'm going to apply what rule to actually carry on with this problem? What's the derivative of x to the 2? Well, it's like the derivative of x to the n. Rule 4. So this will be, Rule 4. I'm now applying Rule 4. That will be 1/2 2x to the 2 minus 1 plus, I don't know how to do that. Pourquoi? I don't know how to do that because this is not x to the n. This is not x to the n, 1/root x. So what do I do with this? First, I am going not to evaluate the derivative, but change this into something that will be called x to the n. Root x is x to the 1/2, and when you bring it up, what do you get? Yes, you get that 1/root x is x to the minus 1/2, and now I can apply Rule 4. So that's 1/2 times 2x plus 2/3 times 1/2 goes in front. Remember, this is Rule 4. X to the minus 1/2 minus 1. Let's continue over here. Good. So minus 1/2 went to the front, and we subtract 1. Why? Because this is Rule 4. What about this? 1/2 and 2 cancels out, That's just x. Here, the 2 and the 2 cancel out, and the 2 and the 2 cancel out, and I am left with minus 1/3 x to the what now? Minus 1/2 minus 1. Calculator, minus 3/2. Good. How many marks for this on 10? You leave this as your answer. How many marks on 10? You think 10? Think again. What's wrong with this? It actually has a negative exponent in the answer. We don't want that. We want our answers to contain only positive exponents. So I need to get rid of the negative exponents. That is not a chore. That is actually fairly easy. So minus 1/3. This guy becomes 1 over x to the 3/2. The negative exponent makes it come down. So that is x minus 1/3x to the 3/2, which is a completely satisfying answer. 10 on 10, 5 on 5, 17 on 17. Here's an equivalent to that. That would be x minus 1/3 square root of x cubed. Do I prefer one over the other? I do not. They are both equivalent. So either this or that, they are both my final answers to this problem. Good. Let us quickly take a look at the proof of this to complete today's video. Well, and we'll see how much time we have for Rule 7, but I don't think we'll actually have time to get there. So, good for this. Let's take a look at the proof. So, erasing all that jazz. And basically, we're proving rule 6. So rule number 6, we are proving it. Okay, so how am I going to start this proof? Remember, like rule 5, when I wanted to find the derivative of k of x, I actually called the function k of x another name. What did I call it? Yes, you paid attention. It's j of x. So I'm going to do the same thing here. J of x. I'm going to call that. Okay, you know, I'm going to do the proof for the plus, and the proof for the minus is the same. All right? So I'm just doing the proof for the plus. Later on, perhaps on an assignment, we can do the proof of the minus. So basically, the question is, j of x is f plus g. What is j prime? What is j prime? I.e., what does that mean? Id est, that is to say, what is j prime? What is j prime? Well, j is f plus g. If you're a francophone, that's confusing, huh? Because in French this is J and this is J. But in English it's exactly the opposite. This is J and this is G. So it took me a few years to get those two straight. Okay, alors vamos. Again, we have no other option to find J prime than to refer to the annoying limit definition of what J prime will be. So as usual, as like in rule number 5, this is j of x plus h minus j of x all over h. Okay, we do what we usually do. We replace by the stuff we know. So let us have, oh, I think I might need a little more space than that. That's okay. Let us replace, let's put the minus here. Let us replace j of x by what we know it to be. Do we know something that we can replace for j of x? Bien sûr, it's right here. J is, going to need a bracket here because there's a minus. So f plus g. And then here comes this guy. Now, usually here, I got to be careful. Yes, as usual, I want j of x plus h. So I want to replace this x with x plus h. So I will want to replace this x with x plus h as well, and this too. All me x's, they become x plus h. So what is j of x plus h? It is f of x plus h plus j of x plus h. Just going to make myself a little room here. Minus all that jazz over h. Once again, we're not going to do it, but if we did, if we replaced h by 0, if we cheated, of course, we would get 0 over 0. Bon, what should I do now? I don't have a lot of options. Perhaps I can take the minus in there and give me fx plus h minus g of x plus, no, sorry, plus g of x plus h. And then here comes the minus. Minus fx minus gx all over h. Okay? Now what should I do? Any thoughts? Anyone? What should I do? There are some like terms, at least in the sense that this is an f and this is an f. So I think I want to group the f's together. This is f of x plus h minus f of x. And then it becomes g of x plus h minus g of x. Those whiteboards are so small. Going to have to move over here. Okay, so we group the f's together, we group the g together. Now, I want to come up with a little algebraic thingy. It is known as breaking a common denominator. See, everything here is on h. So what I want to do, I want to put that on h and put that on h. Just let me show you. So this is f of x plus h minus, oh, I'll never have enough space here. I should give myself a little more room. So let's go over here. So limit h goes to 0. F x plus h minus fx. I'm going to put that over h. And then I'm going to do the same for the g. G of x plus h minus g of x. I'm going to put that over h as well. So the property here is just like if you have a plus b over c, a plus b over c, this is the same as a over c plus b over c. So what is that equal to? Well, we're done. All we got to do is limit of this and limit of that. We take the limit to each one. So this is now equal to, just going to again make myself a little more room. So this is equal to limit of the first plus limit of the second. I'm breaking this down into two limits. So fx plus h minus fx, gx plus h minus gx. And of course, now you recognize this. You recognize this. This is an old face. What is this? This is f prime. Yeah. Plus, oh, I am quite sure that you recognize this as well. What is this definition? Yeah, this is G prime and QED. QED. Sometimes I put the little box, sometimes I put QED at the end of a proof. What have we been able to show? We've been able to show that, what's the conclusion? That the derivative, so conclusion, the derivative of f plus g, the derivative of f plus g, that is simply equal to the derivative of f plus the derivative of g. And that is rule 6. We'll be practicing some more of this rule 6 on the next video. And then we'll actually move on to the multiplication and addition rules for the third video on rules of derivatives. In the meantime, take care.